Good evening, everyone. Hope everyone is ready, and we're going to start with today's presentation. My name is Petar Yanakiev, and I have been doing web development for more than 25 years. I started when the most popular web browser was Internet Explorer 5. So yes, I'm old, and I hope that I can bring something to the table today in this presentation. So thank you for attending. Before we start, I would like to go over some important housekeeping details. This session will be recorded, so keep that in mind. And at the end of the presentation, we will have some Q&A. But before that, I'd like to present that this talk is part of Tech Savvy Talks hosted by Scalefocus. This is the second season of the initiative. Under it, we hold events in various technological topics, and they are presented by speakers from Scalefocus who are specialized in different fields. Stay tuned for more events of the series, and you can find us on Eventbrite. So yes, the session will be recorded. We will have an interactive Q&A session at the end, and you will be able to send us your questions via the Slido platform. You can find the link on the slide. You can use the QR code to open it. And yeah, you can use the Tech Savvy hashtag to find us there. So today's agenda is covering what we do, how we do web development, and more specifically web applications. What could go wrong with building a robust big web application? And can we do something about it? Can we control the complexity and how we do that? Then we will have a bonus that is a surprise, and then we'll have some surprises, other surprises as well. Okay, so let's start. What is complexity? So the definition of the word complexity can be found in the internet, but I have put it here for reference. And complexity characterizes the behavior of systems or models whose components interact in multiple ways and follow local rules. This means that there is no reasonable higher instruction to define the various possible interactions. So the model itself interacts with the rules within itself. In the software, systems are something that is not obvious and easy to grasp by just looking at the code. Implementation is in concern with ownership and structure, and it involves mixed level of abstractions. I know this sounds mouthful, but we'll go over it in just a moment. So what could actually go wrong when we develop a system? Usually when we start anew, it looks quite straightforward. We download something like a library, we have code generators, we have many tools to help us go over the initial state of bootstrapping the application. And mind you, that complexity doesn't happen just like that. It creeps in little by little. So for example, it can start with lack of separation of responsibilities. It looks really easy to put a line of code that does just what we need, exactly when we need it, but it might not be the right place to do it. Maybe we put some files where they don't belong, but it seems right at the moment, or we don't follow specific rules or patterns how we build it. And what happens at the end is that it becomes, the more and more things we mix in, it starts to get harder to reason about, or even to change the code. So basic complexity happens over time, little by little, bit by bit. For example, one example of web development can be that everything, absolutely everything can be put in Redux state. So basically this means that all the component state, everything, not just the data, not just the user data, but also user interactions, also component state, also timers and whatnot, everything can be part of it. And this makes the state very complex. Async operations with state changes within component functions. So So let's say we used something to define our business rules, but then why not just put it here because it makes sense at the moment? We can have multiple state instances. This goes against the, let's say, the rules or the best practices. But I have seen this, and at the moment when we do this, it makes perfect sense. We can add functionality ad hoc, whatever we like it. And all of this, of course, will work, at least initially. But we should strive to do better, because this is complexity creeping in and laying down problems down the road. So what can we actually do? There are multiple solutions, and programmers and developers have been fighting complexity for many decades now. So of course, there are multiple solutions. The most important thing is to choose one that matches the objectives of the project and stick with it. This means that once you choose it, you have to abide the rules and be strict about it. And at points, it will look like it's an overkill or doesn't make sense, but it is important down the road. And also make sure that everyone on the team understands the rules and understands why we're doing it that way. It is important, otherwise people will not be motivated to follow it. And almost invisibly, the complexity will still creep in. So let's dive into some examples to make matters more clear and understand better what we're talking about. So let's have a node application. It is an imagined node application that, as many node applications, will work headlessly. It will provide a semi-simple functionality, but we know that down the road it will be used from the CLI. It can be used also as a cloud function, but also as a standalone service, as a microservice somewhere in the cloud. And it will do something very simple. Let's say it will work with some binary formats. I chose docx, but it's imaginary, so it can be something else. It can be anything, actually, anything that is binary. And we have the task to convert it to some structured data and have it as a database record. It will have to take as many inputs as we have and convert all of them into a single record. So if you have 2 inputs, you have 2 records in the database. Of course, you have to think about duplications and identification of the different duplicates and so on. But this is a detail at this point. And of course, the binary format can have multiple versions, and it can be more than one format. So we have something that looks simple, but with the potential to grow more and more complex over time. So one of the solutions that I really like for writing software in general and keeping it in good shape over time is the so-called clean architecture. It is well known in the industry, and it is well tested in the industry. Bob Martin is one big proponent of it, so you might have already heard about it. Unfortunately, he's not dealing with JavaScript, and of course, we will see that we should adapt this architecture to the web applications and more specifically to JavaScript applications. But still, the architecture is very sane and is widely applicable, not only to JavaScript, but basically to any language and to any project that you might have. So on this diagram, we see a general overview of what it looks like. At the top of the pyramid, we have the entities, which is basically the data that we're working with. And it's an abstract data that is specific to the application. So it can contain all the business rules and all the data that is needed to execute that. The use cases are actually the rules by which this data is governed, which means that it is like executing command over this data. The lower level, the green one, is where we put the adapters. We call them controllers, gateways, presenters, but it's basically, imagine that you have data and you have to present it in a certain way. Most usually we use React or web components or anything else. And below that, we have the external interfaces, links to network, to local storage, to IndexedDB, and so on. And in the case of Node application, we actually, the controllers, we have the routers there, and we have the database links and file storage, and so on. And also we have the responses where it can be rendered as a web page, or it can be JSON response, and so on. So let's see what it can actually, what it actually means, because it sounds still a little bit abstract. So the yellow one is actually the relevant data. Who we're working with? Let's say we have a user, or we have a book, or we have something, an object that is represented as data structure. And encompassing that is what we do with it. What can we do with it? What are the rules to work with it? What is possible and what is not possible to do with this data? And then is the how. So in this green part of the architecture is the flow of action. So let's say we want to record something to the database or something like that. So we'll pass the control to this layer. And in the green one, sorry, the blue one is the tools, the actual drivers. It can be Postgres, or it can be NoSQL driver or something like that. This is the actual implementation of the link to the external system where we want to interact. So basically, it's a provider for access to the outside world. So let's examine how this happens actually. First of all, the call flow is from top to bottom. Each layer has its own well-defined responsibilities. In the middle, we have the use cases and the entities. And then we have the repositories, which are executing commands with this data. And the data sources are actually just the remotes that we're using. It can be the database or anything. So it makes sense that we receive a request over the network. We strip the auxiliary data of this request, and we extract only the meaningful data. We can adapt it or remodel it and pass it to the use case. The use case then work with it, decides what to do, and pass commands to the repositories. The repository can be saving or retrieving data. And then on the lowest level, we have the data sources, the actual implementations of these storages. It can be file system, again, it can be object storage, it can be IndexedDB, and so on. So let's see what it looks like as code. So we have some router. This is a Node application again, and we have some sort of router, and we can receive post requests. And typically in Node applications, we have the request and the response as part of the function call, and we want to unwrap the data first. So what does this mean? It means that we're just stripping at this point, we can have something like authentication and authorization, checks, whatever. But basically, we want to make sure that only the data that we would like to work with is present. So the result in this code is actually what we unwrapped. Sorry, the buffer is what we unwrap. So we are receiving a binary file. It is wrapped in a request object. We unwrap it, and we have only the data. Then we pass it to the controller, which will receive this buffer, our binary data format, and will give us a response, something that we worked and we did something in it, and we transform it and we return something. And then we will wrap this result as a response, so we can send it over the wire. So we can wrap it as JSON, or we can wrap it as XML, or whatever it is. Okay, so this is the first level. This is where actually things happen. And then the controls is passed to the actual controller. So it makes sense to call them controllers, right? But what does the controller actually do? It receives the binary data and does something, and then we have an answer, a response. What would that be? So the controller actually can do several things. One of the important things to do is that it can convert the data to something that is understandable by our business logic. So for example, in our case, it can make some checks into the binary file. Let's see, does it even seems like we have to verify that this is actually valid input. It can be anything, right? So we can perform this here. We can reformat, we can do DTO to entity translation at this level and so on. But basically we end up with something that we are sure that our use case, our business rules can work with. So we have this binary now and we pass it to our use case. The use case does something with it and returns the result. And at this point we can readapt it. Maybe we can decorate it with something. For example, how much time it took to perform all of these actions. And then we return it. So again, previous slide, we pass it to the controller and we get the result. The controller itself actually is remodeling the data, making sure that it's right, and passing it to the use case, to the actual business rules. So this part of the equation is really just the presentation, because it's coming from the Internet over HTTP protocol. But the use case is separated from the business logic, is not related to how we get to this data. It can, as we see later, it can be something quite different and the use case will remain the same. So what is the use case? The use case here is the actual logic, the actual business logic, what we do with that binary data. Well, in our case, we will use some tools we'll use a repository that knows how to handle our binary data and convert it to an XML format. Okay, great. Now we have an XML. So yeah, but we don't work with XML. We actually want to insert records in the database. So what we can do is then we can convert the XML to an actual walkable tree. This means that just like the DOM tree, we can have an XML tree that we can use functions to walk over it. And then we can have a tree walker repository that has the knowledge what to look inside this tree and extract only the data that we need. And let's say that part of the data is the version. And yeah, the code here doesn't say this, but let's say we only support version 1 at this point. And we can then call the storage repo and find if you already have a record that is matching this one. So let's say someone accidentally put this file twice, this binary file twice, and we want to make sure that this is a newer version, it's not the old version. So yeah, we can do that. We can create a duplicate, or we can just save it as a new record. And then we will return what we saved. So at the entrance, we have a binary format, and at the exit, we have an actual record that we put in the database. This is useful because maybe the calling application wants to make sure that we did the right thing. Okay. And what is really a repository? The repository is something that has the knowledge how to perform certain actions by hiding, and it's hiding the details from the actual business logic. So previous slide says that it will just transform from binary to XML, and then it will transform from XML to a walkable tree, and then it will walk the tree and extract a record. The business rule doesn't have to necessarily know all of these details, so we hide them into repositories. And the repository has all the knowledge how to do this. At this level, we usually use, instead of errors, we have failure objects, and that contains information of what went wrong and is something that the rest of the system, the business rules including, know how to handle. So we don't have to keep all type of errors inside the business logic. We just have to know that something didn't quite went well. And the repositories usually use a data source, which is an actual implementation of how things get done. So in our case, convert a binary to an XML string. Okay, and this is the data source. For example, in this imaginary application, we just call to native third-party code that knows exactly what to do with this binary file, but it needs just a little bit of settings and tweakings that know that we want to do this, but in a certain way. Okay. And basically, this is it. We went through all the levels of the architectures, and we now know that each level is responsible for something very specific. For example, how to handle HTTP requests, how to unwrap the data, what business rules to apply, how to operate on this specific data, and how to extract it to XML, how to convert it, and so on. So this is implementation detail. It's covered by the repositories. Okay, so it seems like much, but the more and more use cases we add to our application, it will become clear that this level of abstraction and separation is actually beneficial because it allows us to do something very interesting. For example, our imagined application, as I mentioned, has to work from the command line as well. And how can we do that actually? So the command line usually is started from some sort of terminal where we cannot use the request anymore. The request and response, they do not work on the command line. We actually have to use the arguments from the command line. And what we can do is we can actually add a different controller that will use some let's say node module that can actually extract meaningful information from text input. So let's say the user will pass in the path to the file that he wants to import in the database. We can extract that. But still, it's not, the path is not enough. The use case expects binary data, read in memory. So what we can do in the controller, we can convert it. As I mentioned, controllers can convert data. So what controller can do is actually, it can grab this path and it can try to read the file from the file system. Once it's read in memory, it's exactly the same as if the file has come from the network, okay? And from then on, the code is exactly the same. It goes to the use case, it goes to the repositories, it performs whatever it has to perform. And even the link to the database is exactly the same, no change in code. So the data source stays the same. And then the controller receives the answer from the use case, and it can then, instead of sending it as a wrapped response, it can, for example, console log it. And yeah, so let's say we want to also run it as a server. So we can start it with happy.js, for example, in a Docker container, and we'll have an HTTP listener. Then we'll do exactly what the codes showed. But then again, we can also use it as a cloud function, let's say in GCP. So how can we do it there? So we can utilize the request response again, but we can also set it up as just a function that expects the buffer. So just a wrapper function. The controller in this scenario will just export a named function. So as you can see, we have now 3 types of ways to accept input data and 3 types of ways to return the result, but the actual logic of the application didn't change at all. Only the controller level changed. So we can have additional benefits with this. Of course, we can have better testing because we have clear separation, what happens where. And if we're using dependency injection, we can also have additional benefits. And one of the tech-savvy talks this season is also dedicated to dependency injection, so I will not go into much details. And finally, when we have done all of this, we can actually profit. Okay, let's take a very quick look at another example, which is a browser application. It can be a chat application, again, imaginary one. It can use a REST API, but it will also probably use WebSockets for faster refresh or receiving updates and so on. It's a chat application. And let's say that the application itself is utilizing a third-party vendor as well. Okay, and a technology stack can look like something React, Redux with Dunks, Axios for networking, SignalR for WebSocket, IndexedDB for cache. Okay, it sounds like trivial web application that is supporting chat. How could that look? Actually, in the diagram that we saw before, it's sometimes hard to put the exact implementation in the correct place. So what I did is put them named here. So the Redux state with reselect can be the actual entities. So this is the data that we know and we work with. We can have the use case in chunks. So this is what will happen, and how exactly it will happen is determined by the services. So data retrieval, transformation of the data. I often see applications that directly take the response from REST APIs and put it in the Redux store, but this means that if the API changes, we have to change the code all over. So it's usually beneficial to have some sort of transformation and define only the data types and entities that we will actually need it in use. And initially, the converter can be as simple as returning the input, but in applications that are developed over time, it can change quite drastically. And still, the use case will remain the same if you have this type of adaptation. So data adapters and mappers are very useful. We can have the storage and we can have the components in the green zone. And latest, we can have the actual implementation for the low level of things. As I mentioned, Axios, we can have a wrapper for IndexedDB like Dixie or something like that. We can have the sockets. In our case, WebSockets are implemented with SignalR. And the renderer, it can be most probably React if we're using Redux. So yeah. And I think it's very beneficial to have a example code structure for this pattern, because sometimes people tend to not be sure where to put what in order to make sense. So I have done this. This isn't just an example. I think it's quite well done, but you will always be able to adapt it to your use case. So we have these three layers, these three directories that contain all the information that we need. So the domain is actually the actual data that the application needs. This is important. This is not the data that's coming from the REST API, nor the data that's coming from the WebSocket. This is the data that the application needs and uses to process business logic. The use cases, we talked about it a lot. They can be implemented as chunks. And the repositories here are only interfaces. So let's assume we're using TypeScript. The use cases themselves will use, with dependency injection, they will use just the interface of the repositories to perform some actions. Later on in the data layer, we can define the actual implementation. And with dependency injection, we can inject it into the use case classes. So the data directory will contain all the models. So what the model would look like? It can be something that accepts a very simple response from the server that can contain like messages, error would be null, it's successful. It can also contain data. We can extract this data. We can convert it, transform it. For example, we can convert strings to actual dates, or we can convert zeros and ones to trues and false. This is very often seen in REST APIs where the remote somehow decided to use numbers instead of booleans. And the data sources here are actually wrappers around the implementation detail. For example, it can create a instance of Axios that is configured for our specific use case. And we'll expose the get, post, put, patch, delete, and so on methods. The repositories we talked about, and the presentation layer can actually contain our routes and controllers. What can be the controllers in this scenario? It's nice to have these controllers. I explained why before, but what it would look like in a React application. Well, my opinion is that it can be a function that accepts the events from the actual user interaction with the browser, with the rendered tree, and it should receive the unwrapped events, so the data of the events, and pass it into the use cases. This is a question that comes up a lot, so I decided to put it in here. Again, what is DTO? The DTO can be converted to our entities. We should support failures. We have this clear separation of layers. And most importantly, with the dependency injection, we can actually have composition. So we can have multiple implementations of the same thing and inject what we need depending on the use case. So with the node.js application, it was clear. With the browser, it's not so clear, but let's say we want to have something like different renderers. So yeah, you can have a 3D renderer and you can have HTML renderer. And yeah, we can compose this and use exactly the same code, and just the rendering process will be different. Okay, great. Oops, sorry. So, okay, it's time for our bonus. So we see that we have all these layers in stratification, separation of concerns, separation of responsibilities. We have nice structure. If we decide to follow it and we decide to be strict about it, I can guarantee you that we can have a very robust application, regardless of the moving components of it. So for example, what can happen is we might want to change Axios for something else, for fetch, for example, but everything else will stay the same. And because we have this separation, we can test only the parts that we change. But we can also have something else. I call it distributing layers. And what it looks like, what can it look like? Well, we said that we have these controllers, and we said that we can adapt the data coming from the network in it. But imagine that we can get this big chunk of code, and it will become big over the lifetime of the application. And we can actually move it to a separate service. We can move it to something like a backend for front end, or even to a microservice. And then all this logic will live its separate life, and the main application will consume it directly. So something like by RPC or something like that. So you don't necessarily have to have this big monolith when you're following this architecture. You can design it in a way that will allow it to be executed separately. It can be done, the same thing can be done with let's say, web workers. The logic can be separate, but because it's the same app and follows the same strict rules and the same architecture, you will be able to do this without actually writing a new app. It will still act as the same app, even though it's distributed. So I think it's a big benefit.